Do you hear me? Do you hear me?
Yes, sir.
Okay.
Yeah. Okay. Very happy to have Hiraku to give us a part 2 of the.
Okay, thank you very much for coming again. So I introduced also symplectic quiver case last week. So today I only consider the type A case. So maybe I use this one. So SO1. So sometimes it could be O, then SP of W1. So it should be alternating with SO and so on. And this is finite, so it ends like this. SO of N, SP. And I didn't mention, I briefly only mentioned the anomaly cancellation condition last week. Cancellation. So I explained that unless this condition is satisfied, the Coulomb branch is not well defined. And concretely, in this case, for SP of Vi, and you consider the SO of Vi minus 1 and SO of Vi plus 1 and SO of Wi, then this condition means, so for each I such that SP vertex. So this summation of the summations of dimensions of nearby vertices is even. So this is a condition. So this condition will be played. Roll some roll later. Okay.
What concretely goes wrong?
Oh?
What concretely goes wrong? You say Coulomb branch is not well defined. What happens?
What happens? The definition doesn't make sense, and how to say?
It shouldn't be, right?
So we use, I didn't explain so this requires a general definition. So in our previous paper, so we assumed that so we start with group and its quaternion representation, and we assume in the previous paper, we assume M is of form N plus N star. And if this condition is satisfied in this example, then this condition is automatic. And we don't explain, I didn't explain what is the general condition for this M. So I construct some space, moduli space. Maybe I did not write in this way. So which is somehow over the affine Grassmannian of G divided by quotient G of O. So we consider the modular space, Orthosymplectic homology of this modular space. So first of all, this modular space doesn't make sense in general, but somehow instead you consider so return back to this cotangent case, we consider the so-called dualizing complex on this, and then push forward. So instead of global homology of this, you can consider the constructive sheaves on that. Then you manipulate something on this side, on this affine Grassmannian to make sense, to generalize this definition. So in general, you can construct some constructive sheaf which is defined on line bundle on this affine Grassmannian. So this is not the correct line. So somehow you need to descend this constructive sheaf to downstairs. This is anomaly cancel condition guarantee. So very roughly something like that. So anyways, the Higgs branch is well defined always. And basically, I explained, more or less I explained what is Higgs branch. So this is MH, at least for if all groups are orthogonal groups instead of all SO slash O. I mean, we could have SP. SP is okay, but if we have considered SO or O, then we choose all groups to be O. It is a modular space of SU2 equivalent instantons on R4 for classical groups.
Don't you need a covariance and just some order 2 element of SO2, but not a full group, or you really need a full SO2? In string theory, we're just an order 2 element.
So you mean that the S1 plus order 2 element? SU2 or SU2? So I started with the ADHM description last week, and then I assume SU2 equivalence. That changes V and W to the SU2 representation, and then V is direct sum to VI tensor Y. And if W is orthogonal, then V is symplectic, and then VI for I odd is symplectic for I for even is orthogonal. So we get in this. So if you assume smaller group equivalence, you can still play the game, and in some cases you get this kind of similar description, but maybe not in general. And also by result of Kronheimer, so this is isomorphic to the following variety, mu bar, effect with S rho lambda. So O mu is a nilpotent orbit. Or for this classical group of type mu. So mu is a partition. So this is determined from V dimension vector V and W. I don't give the precise description, but there's some combinatorial expression for this. And S of lambda is slowed with size. To O of lambda. So you get this kind. And if you, so I think this is a simple observation, but I give this observation for unitary groups and in that case we just get the ordinary quiver variety of type A. And the quiver variety of type A is the variety of this form, which is I observed in '94. And the same argument works also in here. And the Kraft processes studied the variety earlier. So this is 1982. So they consider the case when W1 framing vector space appears in the rightmost vertex. So in this case, so this is remark. In this case, the S lambda is trivial. then the slice is the whole real algebra. So then in this case, MH O mu. So Kraft process realized the nilpotent orbit for classical groups in this way, and they use this experiment to study various properties of nilpotent orbits. For example, they determine the normality of the orbit. So orbit is not normal in general. And for type A, it is always normal, and the situation it becomes complicated if you study the nilpotent orbit for classical groups. So recall that in the previous week, I explained how to identify some known space with Coulomb branch. So one of the very important ingredient is the normality of the candidate. And for nilpotent orbit, for classical groups, normality is not true in general. So this is a really delicate problem. So in some case, you must replace Coulomb nilpotent orbit by its normalization, and sometimes by covers.
Just to recheck, you say Coulomb branch is always normal?
Coulomb branch is always normal.
But the Higgs branch may or may not be.
Higgs branch may or may not be.
What does normal mean?
Normal, variety is normal. So well, maybe the first simplest.
There's no regular rational function. No non-trivial regular.
One of the, I think in this particular situation, so if you consider this kind of, so you have the cone, you have A1 singularity and glued at the origin, then this is non-normal variety, which is what is as a nilpotent orbit what it is. I think this is what is SO4 or something, SO4 and some orbit. So this is also instant modular space. That is what it is. So this is something to do with SO4 instanton. So SO4 is a quotient of SU2 times SU2, and you have two instanton numbers for SU2, SU2. But if you regard that SO4 instanton, and if you apply this ADHM, then you only have one integer for instanton charges. So because of this as a SU2 instanton, this is 1, 0. So one of the instanton charges is first factor, and this is for the second factor, and this is an example. The mu and lambda is basically arbitrary. So in order to be this intersection to be non-empty, mu and lambda here is a partition. I regard it as a partition. And in order to this to be intersecting, so mu O of mu must be contained in the closure of, maybe O lambda opposite. Lambda mu are partition, and so you consider something like this. So this is of mu, and this is of lambda, and you choose transversal slice. you have a point here, take a point in here, and you choose transversal slice. So this is right. So the AD singularity is an example of that, of this, but you could consider more general intersections. Yeah, this type of singularity has been studied in geometric representations, in particular, its relation to spring representations. Any further questions?
Sorry, you said this mu and lambda, they are partitions, and mu is determined by B and W?
Mu and lambda are both determined by B and W's. Maybe I will give some example. I think it is better to do with example rather than writing down the formula. Maybe so I just say that if the W appears only in the right extreme, rightmost vertex, then we have lambda to be trivial. And maybe the one example which maybe, let me see. For example, 4, 3, 2, 1. In this case, I think that mu is just this is the regular nilpotent of it. I think this is well known. Okay, I explain Bohr varieties, also symplectic Bohr varieties. So what is the goal of this? So I don't give the very general result, most general result, but basically we prove that Coulomb branch. So this is theorem in progress. Coulomb branch of also symplectic is also symplectic overlap. And also symplectic Bohr variety is defined for some combinatorial data like dimensions like this. And for given V and W, I define the combinatorial data for that and define also symplectic Bohr. And for here, I take all SO group to be is SO. We don't use O because once you know the Coulomb branch for SO, then the Coulomb branch for O, if you replace sum of SO by O, then it is the quotient. It is the quotient of the Coulomb branch for all SOs. So it is enough to assume. On the other hand, so as recall, for the Higgs branch, it is most natural to take all the groups to be orthogonal group. And for others, it is a cover. Sometimes, for example, in this case, you get the cover of nilpotent of it. This is still an interesting space, but less well understood. So I give the definition of also symplectic Bohr variety. So also symplectic Bohr variety, as in the case of quiver variety, it is symplectic reduction. Or in this particular case, you can consider hyperkilometric on this. So you can consider this also as a hyperkilo reduction of a product of two types of symplectic manifold. So if you know the definition of varieties, then it is very similar. Variety is symplectic reduction of product of two types of symplectic manifold, and those two types are slightly different from the original variety to orthosymplectic one. So two types. First type. So maybe I use this combinatorial diagram, plus and minus. This is V1 and V2. So plus stands for SO minus SP. So this is C of V1 tensor C of V2. And you have an action of SO V1. So plus is SO times SP of V2. So maybe I also recall ordinary. So we consider this. Maybe I should replace this by branes, but this is either NS or D5 branes, and these are D3 branes. So this is bifundamental. Okay. Second type is a little bit more complicated. So second type has further separated in two types. So either minus. Maybe I should also say, in this case, you can also have the opposite one, minus plus. But this is the same, you just replace SO and SP. But for second type, both must be plus or both must be minus. So this is the modular space of solutions of Nernst equation on the interval maybe minus 1, 0, 0, 1. So 0 depends this cross, and 0 is the singularity of the solution. And on here you have SO V1. So Nernst equation is a equation for connections on these intervals, and you consider S of V1 bundles on here and S of V2 bundles on the right side. And the equation is just dimension reduction of the instant equation with matching condition. At 0. So this is a pole. So basically, for example, if V1 is greater than V2, then the solution T alpha looks like. So T alpha for left, T alpha is 1, 2, 3 of right plus of T and rho alpha divided by T plus of 1 and sum of diagonal. And rho alpha is rho alpha, rho 1, rho 2, rho 3 defined homomorphism from SU2 to SO of V2 minus. This is the real algebra homomorphism. So I identify this to be. And this modular space has been studied in stars is sun. Of I don't remember T of something. So this part vanishes at T equals 0. Cross is NS5 plane or D5 plane. So there's no meaning at all. So this is just notation. And this one is also similar, just SP. So in particular, somehow you cannot because we have need to some relation between the left solution and the right solution. You cannot change the type of the real algebra from SO to SP. So this is if this is plus, then this other one is also plus and minus. On the other hand, for the first case, the type must be different. So we consider the tensor product, and this must be symplectic vector space. So if we consider the symplectic vector space and orthogonal vector space, the tensor product is symplectic, right? So this is symplectic. Maybe I should. This is symplectic. Or this is the quaternion vector space. So this is flat hyperkähler manifold. This modular space is also, I should say that gauge equivalence. I took the trivial gauge transformation is identity at the end of this interval. Modular gauge, which is gamma plus minus 1 is equal to identity. So you have the residual action. So this is modular space is a hyperkähler manifold. And for the ordinary case, you just consider S instead of SO, you consider the unitary groups. And this modular space has been studied in mathematics literature, in particular Bielawski. Maybe it could be known earlier. So this is what it is. V2 plus plus. This is, so if V1 is greater than V2, SO of V1 cross. Maybe I should also say this is this OSP. And if you further embed it in the unitary or in general linear, maybe. So this must be irreducible. So this must be irreducible representation. Irreducible representation with U2. And then it means that irreducible representation has either orthogonal form, bilinear form, or symplectic bilinear form. So then it means that V2 minus, so in this case, in the first case, you also have, in the second, in the first case, V2 minus V1 must be 1 modulo 2, must be odd. So this is one requirement. And for this is, so in my convention, both V1 and V2 are even, so V2 minus V1 equals 0. So this is trivial, but we have those requirements.
It's a condition of this.
Unless this condition is satisfied, this space is empty. So this will play some role after. So this is the so-called equivalent Rhodes slice. So this is equivalent. I mean that if we cross this one, equivalent Rhodes slice. Or maybe this is a hook type partition. So you have V1 minus V2. And similar, just to change V1, V2. And V1 is equal to V2 cannot be happening in this case. Right, this principal nilpotent object for V1 minus V2 correspond to this embed.
So what is the T alpha and T alpha R?
T alpha is the solutions of Nernst equation. So this is this depends on T. T is a coordinate for this interval. And you have the connection, and also you have three Higgs fields, T1. So
is the little t a parameter?
Little t is a variable. So it is defined on this interval.
So t is negative or?
T is minus 1, 0, or 0, 1 in between.
So TL can only receive the t.
TL means that the t is negative here.
You must have TR is on the right interval.
This is 0, 0 to 1.
But you have a matching like so the confusion was like t for the red hat solution the t is negative or positive.
This is t negative. But if when t goes to 0, then it behaves like this. So this diagonal part is continue to extend the solution to right side, right? This part. but this diagonal, this block part has pole of order 1, and this pole satisfies the how to say commutation relation for SU2.
What's the divergence of behavior of this Ti when t goes to 0? When little t goes to 0, how does the capital T diverge? Is it also order 1?
Capital T order 1, this is.
Okay.
And this off diagonal part vanishes at t equals 0.
And you're saying from this condition you can deduce V2 minus V1 has to be odd.
Well, I mean, this is very simple condition. So we have rho alpha. This residual part to define the SU2 representation. If you embed this SOSP the algebra to unitary algebra, then this is an irreducible representation of SU2. So the symplectic orthogonal is determined by the dimensions. So this is basically what I said. So this is SP of V1 times S of V1 minus V2, 1 of V2, and V1 and V2 exchange if V1, V2, if V1 less than V2, and one remaining case. So this is a little exceptional case if V1 is equal to V2. Two cases and T star of SP V1 and C of V1. So this is the result of analysis of the solutions of Nahm's equation. And those parity conditions for V1 and V2 can be also seen from this description. So nilpotent orbit for general linear group, nilpotent orbit corresponds to partition, and you have a similar parameterization for orthogonal and symplectic groups, but you don't get the arbitrary partition. So if you have, so for example, in this case, I think if you have V1 minus V2 in this case is even, so even part can appear arbitrary way, but if you have odd part, then odd part must appear in even times. So if V1 minus V2 is odd, then it appears only once, and that contradicts for the condition for nilpotent for SP. And for orthogonal groups, the condition is opposite. So anyway, so you have these conditions, parity conditions. So combining those building blocks, use these building blocks and take product, and if you have common group, maybe did I say that there's group action, and yeah, maybe it's not so. In this description, you must be a little bit more careful how to see the group action. So SOV1 action here is clear, and you have SOV2 action, but basically SOV2 action comes from here because we consider the trivial nilpotent orbit for SOV2. So anyway, so this is a symplectic manifold with SOV1 times SOV2 or SPV1 or SPV2 action. So you consider product of those, and if you have a common group, then you can take the diagonal reduction. So this is also symplectic overlap. This case?
Yeah.
So left multiplication and right multiplication. And for CV1, I think only left or right.
How do I know which one is right?
This is a convention we draw in this way. And left is less. I think that when you act on this face, then yeah,
That description is completely symmetric, right? It says they include.
yeah, this is completely symmetric, but somehow you need to trivialize the gauge transformation, and then you solve some ordinary differential equation. Then you solve from left or right. So this makes difference. So the proof is, I mean, this is a how to say? So use this hitching type correspondence for this, the result of this Bielawski. So if you enlarge the gauge equivalence from the unitary or SOSP compact group to this its compresscation, then the equation becomes trivial. So that is the thing. But since this has singularity, so you must analyze the behavior of singularity too. But basically, because the equation becomes trivial, you can solve the ordinary differential equation. So this is how you get this expression. Anyway, so this is very much well established to result in maybe in 90s, starting from work of Donaldson. Okay, let me think what. So I say one thing, Hanany Witten transition.
Was that clear? So you had some quiver, right?
Mm-hmm.
And so what's the convention to? So you had some quiver for this quiver gauge thing, right?
Mm-hmm.
And now we need some kind of bow quiver with crosses.
Mm-hmm.
So what's the?
It's a little complicated. So I don't want to yeah, maybe. I don't want to, it's a little complicated than type A, so I don't want to explain in full generality. But maybe if you just for ordinary quiver gauge theory of type A.
No, type A.
So MC of so Coulomb large form. So in this case, you consider this one 0 V1 V1 and V2 So you have W1 times, and you have W2 times. So this is a recipe, the Coulomb branch of this. So we put orienting for the planes to somehow, so we replace this by those pieces. But because of this condition, there's some slight complicated issue. And in order to have a correct answer, you must modify the rule. So this is a little complicated, so I don't want to explain.
Your theorem is for any quiver type A.
Or only for type A or affine type A.
So what's the plus minus sign below?
No, this is ordinary Coulomb branch. Type A case. It's the ordinary case. There's no plus or minus. And for plus or minus, if you have plus or minus, it's very too complicated. This part becomes a little complicated. Maybe I continue to this. So if you are not really happy with this computation, maybe this, if you instead the Higgs branch, and then this is, so you just exchange circles and cross. This is, so this is B1, and this is 0. Maybe I cannot distinguish 0 and circles. This is 0. How should I write 0? So if you have cross, this is the case when the corresponding orthosymplectics, we have this one. But for the ordinary case, this V1, this is T star of GL V1 times CV1 times C of V1. Still, this symplectic vector space. But if you take the symplectic reduction of T star GL V1 by GL V1, then this part disappears. So then you take the product of this, and then this part is changed to this one, C of V1, C of V2, and you have C plus C double 1 times. So you get to this part. And so this duality exchange mirror symmetry, 3D mirror symmetry is a realization by brave brains, and you exchange, so as I briefly mentioned, these cross and circles are NS5 and D5 brains, and they are exchanged. So then Higgs branch and Coulomb branch are exchanged. So this is a physical state. This is the argument for Hanany and Witten, how they determine the quiver gauge series, Coulomb branch of quiver gauge series. Any question? So I mentioned that last week that so we don't have a good way to speculate what should be the candidate for the Coulomb branch. But once we know what should be the candidate, then we have some tools to prove this statement mathematically rigorous way. So for ordinary varieties, for ordinary quiver gauge series, we do for type A, we did use this result of Hanany and Witten, and for orthosymplectic, Hanany and his collaborators studied orthosymplectic quiver gauge series also, and we use just their candidate as a candidate, and we checked. Okay, so what I want to say. So Hanany-Witten transition. So this is a useful tool to understand, to compute the Coulomb branch.
Sorry, I didn't understand.
What?
You do have the analog of this prescription for
Also simple. Yeah. Maybe Hanany is may not be precise enough, but yeah.
I see, so the story isn't finished yet.
We make, so because strictly speaking, they have some candidates, but I think it's not precise enough.
I see, you can't prove things that you hope.
Sometimes I somehow change slightly, but not big change. Basically, because so they wrote down the orthogonal brane diagrams, but it's not really, how to say, rigorous object. So we must somehow have correct mathematical rigorous interpretation of their pictures by branes, and then we end up with this. Also, for example, so sometimes the normality is not true, and also some cases what was it's in some cases it's not it's not, so like in the example which I draw here, it's not irreducible. So you must interpret it, the picture appropriately. That is what we did. Let me see, Hanany transition. So what it is. So we have the following diagram: V1, V2, and V3, and it continue to left and right. Then this is isomorphic. So you exchange circles and cross the NS5 branes and D5 branes.
And your understanding of infant moduli and things like that is not good enough to pin these things down?
Yeah, so normality is not as I said, if you just consider the instant modulus, normality is ended. This is a little bit.
Even in type A, the way to understand the brane pictures really work is to understand the corresponding geometric statement in terms of A circle or A and singularity. And then you can say, okay, now I can, because I understand A and singularity, which is weakly coupled conservative string theory, I can run along with the brane. And I would have thought that the right thing to do would be to repeat this for this orthosymplectic case as well. Because again, you're going to get some weakly coupled prescription, which I think.
For normalization part, it is fine, but for by fundamental, this is a little delicate point, and
diverges at that point. In other words, we really don't understand standard string theory there. So you have to go to some place where you do. And I think that's why. I would. That was the word that sat down and they said, okay, your prescription, okay, we understand how it comes from conservative string theory. And that was a wonderful thing. So you just want to repeat that or like.
Yeah. Yeah, I don't know how to explain. And I think one thing which, at least one thing which I didn't understand well was that this distinction between the orthogonal and the special orthogonal groups, and they must be carefully distinguished. Otherwise, as I said, the Coulomb depends on these choices, and how to distinguish them in terms of branes, I don't see, for example. And another is. So I have the corresponding part in orthosymplectic case, and this is against some intersections of nilpotent. In type A, it's against intersections of nilpotent orbital and slices. But if you just consider the similar thing for orthogonal or symplectic, then this is not, in general, it's not irreducible. So you have, like in this case, you have two irreducible components. and it's not normal, so it could not be the Coulomb branch, at least in our definition. So somehow we carefully choose what should be the correct variety in that case.
I think in particular, the technology to do this is there. When somebody else did that, actually do it. I don't know. I don't know if it's been done. You would know. You want to consider a rental.
Yeah, I don't know. Okay, what is Hanany transition? You still? Is it okay to continue? So Hanany transition says two Bow varieties are isomorphic if this condition V prime is equal to V1 plus V3 minus. So for example, so if you have, maybe I show the usage of this Hanany transition for ordinary quiver gauge cell case. So this is as a Bow variety. This is one, two, 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 one, two, one, 0, 0. Then I move these circles to the right. And then you compute the linking numbers, and then this is, if I don't make a mistake, this is one. Yeah. So then, so this is, so you have equivalent slice for this. And for this, you have a nilpotent orbit. And this is nilpotent orbit part is partition. So this is the principal nilpotent. So 4, and this is 2, 2, S of 2, 2, 2. So you compute in this. Okay. So examples of Coulomb branch, orthosymplectic gauge series. So first we consider pure G theory. So G is SO OSP. Then it is well known that the corresponding Coulomb branch is so-called universal centralizer. Of the Lagrange dual group. So this is Lagrange dual. So this is also known as the modular space of, I mean, this is the true for arbitrary G, modular space of solutions, not solutions of Nern's equation. For G check. So in this case, you have pole at the this is pole, regular pole at the left edge and right edge. So in this language of Bohr varieties, so this means that the orthosymplectic Bohr variety associated with so 0, V plus or minus. Right? So if you start with SO of 2k plus 1, then Lagrange dual group is SP 2k. So SO. And yeah, maybe in this for this particular case, if you replace SO by O, then for this case, I think it's not the Coulomb branch is not changed, but for this case, the Coulomb branch is a quotient of G is a quotient of this universal. So we have this kind of delicate difference for if you replace sum of SO by O's. So this is the first example. So B. So this statement is somehow. So if you have this part like this, so 2n and 2k and 2k prime. So it continues like this. So then you should replace this by orthosymplectic Bohr variety, maybe. Bohr, I draw a diagram here. So what should be the corresponding diagram? So by this recipe, somehow if you have this, then it should be so this is SP of 2n. So the corresponding group is SO2 2k plus 1. This is SO2k plus 1 2n plus 1, sorry. And for 2k prime, this is SO2 2k prime. So then Lagrange dual is SO2k prime. So this should be SO2k plus. And this is SO2k. And this is somehow, if you use the brain picture, then somehow how to say, the brain is drawn just like in these diagrams, and so in order to compute the duality, you apply the duality for each segment of both varieties. So somehow this, from this perspective, it is very natural to get this diagram. So you just replace 2k prime by this Lagrange duality. Right? So with this, this statement is somehow manifesting if you realize the orthosymplectic quiver by orthosymplectic brains. But if you just you use mathematical definition, this statement is not trivial at all. So you must prove, but it turns out this can be proved. And then you go to a bit more complicated case. No, yeah, more. See? Okay. MC of. So if you the vertex is if this SP vertex is surrounded by odd SOs, then somehow you cannot naively apply the same recipe. Because for 2k plus 1, you must replace orthosymplectic of. So for this part, S you replace S of 2k plus 1 is Lagrange dual, which is SP of 2k. And for here, this is SP of 2k prime. And if you just naively apply the Lagrange duality, so this is SP of 2n, so this should be S of 2n plus 1. But as I emphasize that you cannot have this building block because this is coming from the solutions of Nernst equation, and the left interval and the right interval should have the same type of real algebra. So this is not allowed. And in this case, so in orthogonal brains, you distinguish. So there are two types of orthogonal brains which correspond to SP of 2n. So they are different ones. In this case, the Lagrange dual group should be understood the original one. So you should instead of SP of 2n plus 1, you should put SP of 2n here. No, this Hanany thing makes sense only when there's the two by fundamentals. This is I don't know. I don't know how to explain this in mathematical rigorous way, except that otherwise this override also infective override doesn't make sense. But they Hanany and his collaborator distinguished two types of orthogonal. No, I don't do that. So starting from building block, so somehow I separate into pieces, and I apply the some ansatz to each pieces. Then depending on, so here it is the simplest case. If I have some framing, then it becomes a little bit more complicated. And the recipe is different for case by case. Yeah. For each choice of this kind of vertex with framing, I have different recipe.
So what's the rule? The plus node corresponds to SP or SO, or
so for here, naively, you just replace. So this is if this is plus, maybe I should write this is SO2K plus 1. This is P2N. So this is SO2K plus 1, right? Plus minus plus means that this one. Then I replace this by Lagrange dual group, naively, because for pure gauge theory, this result is this is already known. This is mathematical rigorous result. But miraculously here in this case, somehow you should not replace SP2N by its Lagrange dual, but you keep SP2N. Otherwise, the variety doesn't make sense, and there's some physical explanation for that. And C prime. So if you consider MC of plus of minus of plus, and this is 2n, and this is 2k plus 1, and this is 2k prime. So now you have a trouble. So then the corresponding one is, so you want to, so this part is S. So this is SO2K, so this P2K. So this part is SO2K prime. And here you cannot put either SP or SP SO, because then you have you violate the rule for this building block. So you cannot have. Yeah, that is just I tried to say. So both are not allowed. But I didn't explain the anomaly cancellation condition. This violates. So I don't have proper I didn't give a proper explanation of the anomaly condition. But certainly from this recipe, that if this happens, then it fails. Our recipe fails. So this is one explanation why this anomaly cancellation condition is important. Okay, let me give some examples. So maybe so this is, so for quiver, ordinary quiver case. So if MH, so as I said, MH is always like this, or mu bar. I used. Yeah, maybe I implicitly assume this. Yeah. So this is under some condition, mild condition, which I don't explain properly. But also in some under mild conditions. So MC Coulomb, corresponding Coulomb branch is, you just replace the two partition by its transpose. So this is, I think this is the best understood. So I apply some this kind of diagram, but I can correct circles and cross into left and right like this. But you can switch. So this is, if this is MH, then MC is just you can obtain the corresponding Bow variety, but which just exchange circles and cross. This is, you exchange circles and cross. And the Hanany mitten transition is also compatible with change, so it means that it is isomorphic too. Maybe the number is different. 3 and 3. Then I interpret this part as the orbit, and this part to be slice. And then you just change the orbit on the slice. And you also carefully read off the dimension partition, then it is replaced by transpose. So this is somehow manifest from this brain picture. And we want to have similar result for, so this is an example. So we want to have similar result. We consider similar result. For classical, orthosymplectic case. So I just give you some example, illustrate some example, which is in fact rather delicate. So we consider the following one. So the ordinary is nilpotent orbit for SL4, and the corresponding Coulomb branch is so the transpose is trivial, so you just get. So this is all. So we want to make this example to also symplectic one. So we consider minus, plus, and plus, and this to be plus. By some reasons, we need to, instead of 1, we need to replace this by 2. So replace this one. Otherwise, the Coulomb branch is not correct. Then we consider the corresponding Coulomb branch. So MC of above, also symplectic of, so what it is. So for 2, you have 2 circles, and you have so you have sp2 in the middle, so this should be SO3, and here SO3. And if you have a framing, then we should replace it by fundamentals. But by fundamentals, we should the one factor is SO, then the other factor should be SP. Right? And in the original orthosymplectic, ordinary quiver gauge cell case, the dimension of here and dimension of this are the same, but we cannot have SP of 3. Right? So the SP in my convention, SP should be defined only for even. numbers. So then I replace this by sp2. Then next one is SO2, so this should be, next one is SO2, and SO2, and it must end by 0. But as I said, I also said that if you have this building block, the difference of the dimension must be odd. So you cannot put SO 0 here. So SO 0 is not allowed. So instead you add one more. So this kind of somehow ad hoc change we apply quite often. SO2, SO1, and 0. SO0. So this part is replaced by this. And this part also. And then you apply the Hanany transition. Maybe I didn't say that Hanany transition also makes sense for orthosymplectic case. So then what should be the result? So this part? In terms of this kind of non-pole. Non-pole? Zero is just rank 0. So this. But also SO1 is also 0. SO1 is the how to say SO1, but in terms of the equation, how? The modular space is a point, and I don't have good explanation why I got a point. Let me see. T star. This is. I think this is T star of SO1. In this particular case. Huh? One by one. One dimensional. What? I think the TR alpha is 0, and but the connection is trivial, and you have the gauge transformation, which is trivial. So this modular space is a point. This is correct. So this is a trivial. I think trivial connection here. Trivial connection, and also Higgs fields are all vanishes. So this is a solution. I think this is a solution. What's the linear of the quiver? What's the linear rule of the quiver? So plus minus. So the ATAC is human before, plus minus before, and then what here? For orthosymplectic case, I must think about it. So Mira is not gauge theory in general, and no. Let me see. This is let me see. In fact, by this replacement, I think that the Higgs branch is not changed. Higgs branch is MH is O4 S of 2, but 4, 4, 4. This is SP of 4. And we compute the Coulomb branch, and I'm not sure. So Yeah, I think I must sit down and consider what is it. So 0, SO1, SO2, SO3, SO4, SO5. Something's wrong. Maybe I keep one. And this is SP2 and SO1. And this part is T star of SO5. So if the dimension increased by 1, then this is a slice to the trivial nilpotent of it, which means that equivalent slice to trivial nilpotent of which is T star of SO5. And for this part, this is something similar to the orthogonal nilpotent for SO5. The difference is 3 and 1 and 1. But this is not quite correct because in order to apply the Kraft process, so if this is O1 instead of SO1, then this is the nilpotent orbit. But we have SO1 because of the Hanany. So you have double cover of this one. And it's affinization. So in general, so in this kind of examples, more generally, so if MH, if so we choose for appropriate choice of the principal. For SO even or SP S of lambda. So we have some examples of this kind. The Coulomb branch is S of some cover. The Coulomb branch is the some nilpotent cover of some nilpotent orbit, maybe affinization. Yeah, I must finish. Yeah. Sorry. So yes. So this is a little bit complicated. So in the original case, lambda, we just take the transpose of lambda. But this is d of bs is Barbosh-Bourgon duality between the SO of even to SO of even nilpotent orbit of SP even space for aught. So this is the some generalization of the transports for of the partition. But as I said, there is some restriction on the on the partition, allowed partition for even SO and SPs. And if you just take the transpose, this condition is violated. So then somehow you need to take the corresponding transpose, and then somehow you choose the allowed partition, which is small, which is smaller than that one, but the largest among the smaller, which is allowed for this SOSP. So anyway, so this duality between it has been studied in duality between the nilpotent orbit has been studied in the geometric representation of theory or geometry of nilpotent orbit. And in particular, this duality is not the duality, although this is a duality. So so for example, in this case, so this is not identity. So in fact, D of BS is not surjective, and the image of this is called special nilpotent orbit. And this appears originally in Lustig's works, and one of very difficult concept which I still don't understand its meaning. So one definition is image of this one, as I said, the combinatorial way to define DBS. But anyway, so this nilpotent orbit for classical groups have some delicate issue which is not true, which is true for type A, but which is no longer true for classical groups. But somehow this orthosymplectic quiver really see this kind of delicate point. Okay, thank you for attention. I stop now. This is more difficult. So in the ordinary quiver case, we have the description of the quantity deformation quantization by difference operators, and that doesn't work. For the case of Jordan quiver, which I mentioned in the last week, in that case, this method does work, and we get C check C daha in that case. But for this case, basically because we discussed the non-cotangent type case, so this difference operator, it seems we don't have realization by difference operators. Somehow, the difference operator mean that we have the, how to say, some kind of deflection for the cotangent type condition, which I still don't quite understand well. But anyway, so the difference operator cannot make sense. And then we don't know how to analyze the deformation quantization to Coulomb. I mean, it makes sense. The definition is here, but we don't have any concrete realization of this deformation. So we don't have any way to understand deformation quantization. But that is the Jordan quiver case. And this is Jordan quiver case, and it doesn't apply to this case. So for ordinary quiver case, we get the so-called shifted Yangian, and we should get something similar here, but I don't know what should be the corresponding algebra.
How about just for the very simple case that is inverted centralized? Is there you have description of it?
This is Toda system.
In terms of its coordinate ring, as you had, does this exist?
What?
In the very simplistic example with pure H space, is there a description of the space just in terms of its coordinate ring, the way you were able to do in type A?
What do you mean by the
Just no, as a
pure history is like all well like the
It's known.
It's no, anyway, so this is well-known space. The universal centralizer is what? So there are several weights. So you have the pairs of the D group element and the Lie algebra element that commutes, and it's modular conjugacy. And also in that case, for exceptional case, I'm not sure you can. For SO groups, you have minuscule operators, and you have the description by difference operators. And for SPs, it's a little bit more difficult. There's no minuscule weight, but still you can write down the corresponding.
SP has a
SP or language.
I think they
so that corresponds to connected.
all of them SP, they each have a Finkelberg score.
Well, the trivial one you have, but the connected, it's corresponding connected component of the affine Grassmann loop group or affine Grassmannian. For SP is simply connected, so you don't have. For SO, it is you have two connected components, and you choose the minimal one.
Okay, just one more.